All right, let's take a look at kind of an overview of section 3.3 from the Heart of Mathematics, an invitation to effective thinking. Section 3.3 is called the missing member, and it's George Cantor answers, are some infinities larger than others? I know you're capable of reading, but we're going to kind of read through slash discuss these two first paragraphs, and then I'll overview the rest. So around 1872, the German mathematician George Cantor shook foundations of infinity when he proved that the set of real numbers has more elements than the set of natural numbers. In other words, he proved that infinity is not one size, but that some infinity is more infinite than others. At first, such a notion might seem nonsensical. When we have reached infinity, we can't climb any further, right? Infinity is a symbol for beyond any number we could think of. But Cantor showed that there were yet higher mountains to scale. All right, so this, like, it totally makes sense, right? If we think about our natural numbers, we have 1, 2, 3, 4, blah, 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 blah. That's a 4, not a 9. In real numbers, we have 1, we have 1.1, we have 1.3, we have 1.1415952, blah, 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 blah. We have 2, we have 2.001349. Like, I could just keep going, right? It makes sense that 1, 2, 3, 4, the natural numbers, it makes sense that they would be smaller than what we call the real numbers. All right, so real numbers are natural numbers with an N. Fanciness, because that's how mathematicians roll. It totally seems reasonable, but no one was able to prove it until about 150 years ago. Like, while it seems reasonable, yeah, of course, there's more real numbers than natural numbers because the real numbers contain the natural numbers and more. But to show that the real numbers are more numerous than the natural numbers, Cantor focused intently on what it would mean for the real numbers and the natural numbers to have the same cardinality. This is a common mathematical proof. I'm pretty sure that A happens. To prove that A has to happen, I'm going to prove that if A doesn't happen, the world breaks down. Right? That's the mathematician's general approach. So he focused on cardinality. It would mean that the real and natural numbers could be put into a one-to-one correspondence. That's stuff we learned about in the early chapter 2, coming back to keep us going. Right? Very important in mathematics. Writing down what such a correspondence might look like gives us a visual clue as to why any attempted correspondence between the natural numbers and the real numbers could not include every real. Some real is missing, and that's how we get the title of this section, The Missing Member. Okay. Ooh, I had a joke right there, but since I want to keep this as a lecture video, I don't know how that would age, and I'm not going to say it. All right, so from bizarre to intuitive, this is a good read. All right, mathematicians are like jealous little middle schoolers, right? They have egos, they have hormones out of control, but they're like middle schoolers with their crush when it comes to their work. Cantor, like Galileo, was persecuted for his correct findings because people are like, no, it can't be. I don't believe it. I can't see it. I don't understand it. You're smarter than me. You must be wrong. So from bizarre to intuitive is it's an interesting read, but it talks more about the man and about mathematicians and gives you kind of an insight into how human we really are. Weird humans, but we're still human. So, unequal decimals. All right, this is a totally easy concept, and I mean E-A-S-Y. I almost spelled that wrong, E-A-Z-E. It's an easy concept, and I mean easy. But who would think of it? Why would you use it? What it's used for? That might be a little more challenging concept. All right, but what it comes down to is you can tell that two numbers, all right, this whole unequal decimals, if you have 2.314 and you have 2.324, it comes to fact that right here in the second decimal place, since those digits are different, they must be different numbers. That's what this is all about. All right, but we're saying it in a general way, and it's the key to Cantor's reasoning. Okay, so that's all this section is saying is that, look, If we know for sure that in in the second decimal place these numbers are different, then we know for a fact that these numbers are different. All right, so now the section called Too Long Lists. Cantor wanted to compare the natural numbers to the real numbers, right? So he tried to make a one-to-one correspondence. But when you make a one-to-one correspondence, you're very precise about how you make it. That way it comes out in a well-behaved manner. And when he did it in this very ordered way, which you can read through, right? What he found was a missing real number. Right? He found that in this one-to-one correspondence, most of the real numbers are still left in the barrel, right? As we expected, right? But now he's proven it mathematically. A missing real, so this is like, are we sure it's missing? And so we could check our work, all right? Make sure that, if the first real has a 0.2, then we'll use our M value as a 0.4. If the first real at the decimal place is anything but a 0.2, then we use 0.2. All right, so we check our work, we make sure everything's good, and this verifies Cantor's theorem. All right, so read through it. There are more real numbers than natural numbers, and this is a good read too. I believe the project I have for you here, the activity. And I think this is the activity I asked you to do. All right, so this is the optional activity. All these optional activities, I'm telling you right now, they all come from the book. I didn't make them up, but they're interesting, kind of more involved problems than just the exercises that I ask you to do when you have, 5 to 8 of them. So in a small group, discuss and work through Cantor's argument showing that the set of real numbers has a greater cardinality than the set of natural numbers. Let me rephrase that. In a small group, being either you or someone you choose to talk to, read through this section, talk through this section, make sure you understand the proof, because that's what the entire section was. After you discuss it, after you think about it, now what I want you to do is explain to me Cantor's proof, but use your own words. You don't have to be all mathematically specific about it, right? Because you're not a mathematician yet. I'm still working on that. I'm going to get you to convert. But write what Cantor was thinking along the lines, along each step, and talk about his work showing that you understand it. So that's the activity. I don't remember the exercises right now, I'll be honest. But if you have questions for them, remember, I'm on Discord, and you can just hit me up, or also, of course, messages. And if you have to, you can send an email to me. All right. I get behind on email frequently. 3.3, this is the last section we're going to talk about in chapter 3. So we're not getting back here to Anaxagoras, but that's all right. That's 3.3 for you, and we're moving on to chapter 4 after this.